This is Conway's Game of Life, and as the title of this video suggests, we will not be talking about this today. However, this game helps illustrate the point. You can't predict what the game state will look a few turns down the road without actually playing out the game. Let me now introduce today's special guest, the Dragon Curve. Now, the Dragon Curve is big. I mean, really big. The curve is continuous, meaning I could draw it on paper without lifting my pen at any point. Now, let's say I started my drawing at the origin of the plane and drew the curve one segment at a time. Now, if I were to pick a random point, asking you which step of the drawing it would be, you could be tempted to think that, as with the Game of Life, the only way to know would be to draw the curve step by step and count alongside. But I want to share with you today that thanks to Donald Knuth, the dragon has been tamed, and we can instantly have the answer to this question. The Dragon Curve had humble origins. It started as a folded dollar bill. Although humble might not be the perfect word, as the men who folded the paper, Bruce Banks, William Harter, and John Hayway, whose name is often used to refer to the dragon, were all NASA scientists. This discovery sparked the interest of the mathematician Martin Gardner, who shared the dragon to readers of the journal Scientific American. In particular, he showed a picture of what happens if you connect 4 dragons through their tails. This may seem like just a fancy drawing, but it will be the key to understanding the property I alluded to. A few years later, Chandler Davis and Donald Knuth wrote an extensive paper on Dragon Curve, which will be the basis of this video. They formalized the dragon construction and investigated many of its properties. So, what kind of complicated origami could lead to such an interesting pattern? It's actually remarkably simple. You just fold a long enough piece of paper in the same direction repeatedly. Then, by unfolding it and setting the angle in the creases at 90 degrees, you can see a baby dragon emerging. The flaw of this construction method is that you quickly run out of paper. Now, this is a reason why we want to extract the essence of this method to be able to generate a way bigger dragon with a drawing process. If we unfold the paper in a flatter way, we can see that there is an alternance of up and down creases. We can write this as a sequence of U's and D's. Can you guess how long the sequence will be after n folds? The answer is 2 to the power n minus 1. Can you see why? Well, let's see. You take the paper and fold it the first time. This creates 2 flaps and 1 crease. Now you fold it again, creating 1 new crease on each flap. Thus you have 4 flaps and 3 creases. Then we add 4 creases, etc, etc. Now we can see how the sequence is constructed. Each time we fold the paper, it's like we're adding a D in the middle. And the process is recursive, as to construct the next step, we repeat the previous step, then add this D in the middle, then take the previous string in reverse order and switch all these into U's. If we denote by Sn the sequence of these and U's after n folds, we can see that Sn is constructed as follows. Sn plus 1 is constructed by taking Sn, adding a D in the middle, then adding Sn bar, which is a reversing and switching I just explained. We can also construct the string S infinity by repeating this step as much as necessary, virtually infinitely. Using this sequence, we can draw the dragon simply using something called turtle graphics, a formidable invention that simulates, well, pen and paper. You guide the pen by telling it to go forward or turn. In our case, we should go forward 1 unit, and at every letter turn 90 degrees on the right if it's a D, or 90 degrees on the left if it's a U. Now this is the first way to formalize the dragon curve, but it lacks more rigorous tool to analyze it. The goal of this next part will be to move from this sequence to a mathematical function, which is more detached from the paper folding and allow us to plot the skeleton of the dragon, meaning its endpoints. This is a sweet goal. However, you might wonder how we can move from a sequence to a function in space. Our approach will be to introduce multiple side functions. Each one will base itself on the previous step. Then, by remarking a property, we will make it independent, giving it a recursive definition. I will not outline all the proofs. You can find them in the paper I wrote in the description below. But I'll try to give you a sense of what each of these functions means. The first function we'll introduce is called d. d of n equals 1 if the nth character of the sequence S infinity is a d, and minus 1 if it's a u. We're basically converting our sequence of d's and u's into a sequence of minus 1 and 1s. As we know that the sequence is constructed recursively, we can see that if n equals 2k, so n is an even number, d of n equals d of k. And if n is an odd number, 2k plus 1, then d of n equals minus 1 to the power k. The next function we'll introduce is called g. g of n is equal to the excedent of d's compared to u's in the first n minus 1 letters, and we set g of 1 equal to 0. Thus, the expression of g of n can be expressed as a sum. Using the previous function we've defined d, we take the sum of d of k from k going to 1 to n minus 1. There exists a recursive definition for g as well, but we won't go into it. We can now introduce the function that will draw the skeleton of the dragon. However, we need to think about where we want the skeleton of the dragon to reside. We have two different approaches. One of them would be to contain the dragon into one square of space, setting the beginning point to 0 and the end point to 1, and having the dragon zigzag into this small space. This would lead to the creation of the dragon fractal, but this is not the goal of this video. The other choice, the one we'll explore, consists of putting every endpoint of the dragon, each vertebrae if you will, to one point with integer coordinates. As we are in 2D space, we can use complex numbers. One kind in particular known as the Gaussian integer. Gaussian integers are all the points in space with integer coordinates. They are written as a plus bi, where a and b are both integers. Our dragon function, delta, will also be defined as a sum, precisely the sum of I to the power j of k, from k going from 1 to n. So how is this function able to plot the dragon? It obviously takes an integer as an input and output a Gaussian integer. And if we look at delta n and delta n plus 1, we see that the resulting endpoints will be next to one another, as we are only adding either 1, minus 1, I, or minus I. Furthermore, we can see that the difference between g of n plus 1 and g of n is d of n, so they will always have a difference of 1 only. The consequence of that is that two consecutive segments will have a 90-degree angle. As obviously I to the power of an odd number will give us I or minus I, and I to the power of an even number will get us 1 or minus 1. Thus we move in this zigzag pattern. Now I won't detail the passage to the next expression. It's simply using the recursive definition of g to simplify the expression of delta. But let's get to it. If we have a number that is written as a sum of alternating positive and negative powers of 2, then we have this direct definition of delta. Now we know that if we have a number that fits this condition, we can compute delta very easily. by simply evaluating a sum. However, it's a rather obscure condition, and you might wonder if all number fits it. Well, to know that we need to dive into the world of number representation. Would you believe me if I told you that what you think is a number is something completely different? Indeed, what we commonly write down as a number is in fact a sum. The representation we're used to is base 10. A number is base 10 will have all its digits between 0 and 9, and each digit will be multiplied by a power of 10, increasing from right to left. Now, this process can be applied to any base. A number is written in base beta if the digits used are between 0 and beta minus 1, and it corresponds to the sum of increasing powers of beta from right to left. In particular, we can take the case of binary numbers. The alphabet here is 0 and 1, and a number would be written as a sum of increasing powers of 2. Now let me show you a little identity. If you have a sum of consecutive powers of 2, starting from 2 to the power km minus n to 2 to the power km, it is equal to 2 to the power km plus 1 minus 2 to the power km minus n. Indeed, in this example, the first line is equal to 16 plus 8 plus 4 plus 1, 29, and the second line to 32 minus 4 plus 1, 29 as well. We're gonna represent these numbers kinda like binary, using one bar to represent minus 1. You might have realized but this process can generate infinitely many representation for any given number, as you can see here with 13. In order to limit the number of possible representations, we'll follow Knuth's approach and introduce something called revolving representation. A revolving representation is a variation of binary composed of 1 bars and zeros, and the condition is that the 1 and the 1 bar must alternate. We can see there are two representations for one number. Here the two on the screen both represent 26. However, you can see that the last non-zero digit is not the same. The first one as a 1. We'll therefore call this representation the positive one, and the other was a 1 bar. We'll call it the negative representation. Now, to denote the representation, we'll add a 2R to say they're revolving, and a plus or a minus to say if they're positive or negative, for clarity's sake. Revolving representations also exist for negative integers. The leftmost digit simply has to be a 1 bar. Now let's see how to construct a revolving representation. The process will be recursive. Our base cases will be 1 and minus 1. You can see the positive representation on screen. Then, for the induction part, we'll suppose that all integers, positive and negative, whose norm is less than n divided by 2, have a positive representation. Now for the induction part, we have two cases. First, if n is an even number. Well, we can simply take the positive representation of n divided by 2 and append a 0 at the end, effectively multiplying by 2. This gives us a positive representation of n. On the other hand, if n is odd, then we will have to be a bit smarter. We will take the positive representation of minus n minus 1 over 2. That exists because of the induction hypothesis. Then we're gonna negate this representation, flipping all 1s into 1 bars. This gives us a negative representation of n minus 1 over 2. Then we append a 1 at the end. This means multiplying by 2 and adding 1, and thus we have a positive representation of n. This construction method allows us to prove that every number, positive or negative, have exactly two revolving representation. One positive representation, one negative representation. This is very useful because it tells us that the recursive definition of delta we had earlier can be applied to every integer, and thus we can have any step of the dragon very easily. We can even observe that the sum delta gives us is similar to a revolving representation with this alternance of 1 minus I minus 1 and i's. If we rewrite the expression, this is even more obvious. Look, and if we use the bar notation, we can see that what we have is a number in base 1 plus I. In fact, those representations are so similar, we'll say that we have revolving representations for Gaussian integers. Here, the alphabet will be omega and is composed of I, 1, I bar, and 1 bar. And the rotation order goes from 1 to I bar to 1 bar to I. So each time we multiply by I bar. We have even more equivalences. We'll say that a Gaussian integer is even. See, it's denoted differently. If a plus b is even. And this means that the number is divisible by 1 plus I, as an even number is divisible by 2. So even means for the representation that the rightmost digit is 0. We'll also have something similar to positive and negative representation. A representation of z is of type omega if the rightmost non-zero digit is omega. Let's now see how to construct a type 1 Gaussian revolving representation. The process will be remarkably similar to the one we use to construct positive representations for integer. Our base cases, 1, I, minus I, and minus 1, are written here on screen. Now, for the induction hypothesis, we're going to use the norm instead of the absolute value. We want that for all Gaussian integer whose norm is lower than the one of z, there exists a type 1 representation of this integer. Now, as before, we're going to separate into two cases. If z is even in the sense of Gaussian integers, we're going to take the type 1 representation of z divided by 1 plus I, because we can divide it by 1 plus I, and concatenate the 0 at the end, giving us a representation of z. On the other hand, if z is odd, then we're going to take the type 1 representation of z minus 1 divided by I times 1 plus I. This obviously fits a condition on the norm. Then we're going to multiply each digit of the representation by I. This gives us a representation of z minus 1 divided by 1 plus I, a better representation of type I. And then we're going to concatenate 1 at the end. This works because it keeps the rotating property, and it multiplies by 1 plus I and add 1, giving us back a representation of z. Thus, we can have a type 1 representation for any z, thanks to the induction. You might have guessed how we can get the type omega representation of z. It's simply by taking the type 1 representation of z divided by omega, then multiplying each digit of the representation by omega. From this, we can harness a massive property. Every Gaussian integer has exactly 4 revolving representations, one of each type omega. Now I want to draw your attention to the fact that the representation of a Gaussian integer can be divided into two pairs of similar representations. Two representations are called similars if all their digits are the same except for the two last one, excluding the rightmost zeros. So every Gaussian integer has two pairs of similar representation. And the two pairs are dissimilars between one another. They have different digits. You might have noticed in the previous screen that one of the representation started with an I, not with a 1, but our delta function gave us representation starting with a 1 always. Well, it makes sense. It's because there is not just one dragon. In fact, there are 4 dragons. Each can be obtained by rotating the original dragon. In fact, multiplying it by I, 1 bar, or I bar. This is a diagram we saw earlier of the 4 dragons connected to their tails. I hope you understand it better now. We'll denote each of the dragon as a function that generates it, delta of omega, with omega being 1i minus 1 or minus I. We now have all pieces of the puzzle. We just have to put them together to be able to answer our original question. The first piece of the puzzle is our 4 function delta of omega. Each of them take as input an integer and outputs a Gaussian integer. We've also introduced the function that allow us to go from integer to the revolving representation of an integer. and from Gaussian integer to the revolving representation of a Gaussian integer. The inverse function simply consisting of evaluating the value of a representation. Now we would want something that is similar to delta, but for the revolving representation, not the number in themselves. So we'll simply denote it as big delta, and omega will be the first digit of the revolving representation of the Gaussian integer. The way the function works is pretty simple. You simply fix omega, that will be the starting digit of your Gaussian representation, and then you iterate over the digit of your integer representation and follows the order. Now you remember that we have two possible representations for integers. So in order to have a function, we need to specify which representation we want, positive or negative. You can see that applying big delta to the positive and negative representation of an integer will yield a pair of similar Gaussian representations. We can see our function works properly because applying delta 1 to the integer is the same as converting the Gaussian representation to a Gaussian integer. We get the same result. Now for the inverse process. If we take a Gaussian integer, remember it has 4 possible representations denoted by its type, so the last digit. For simplicity, we'll only keep one element of each pair of similar representation. Remember, the first digit tells us which dragon can generate this number. The inverse function to big delta is pretty simple. You simply take your revolving representation of Gaussian integer and iterate over it, writing first a 1, then alternating 1 and 1 bar in the same fashion as delta. Then, by converting this representation to an integer, we finally have the answer to our question. 8 plus 3i is the 67th step of delta I and the 367th step of delta 1. Each point is crossed by 2 dragon. It can be the same dragon as well. Remember 2 minus 3i, both pairs started with a 1, but this is a very interesting property, and we now have the answer to our. I hope you enjoyed this video. Unfortunately, I didn't have as much time as I would have liked to make everything as good as I wanted it to be. However, I hope you still learned a lot, and if you want to learn more, I encourage you to read the paper I wrote in the description, as well as the one written by Knuth and Davis. The next video will dive deeper into the fractal object of the dragon curve, or maybe in the fascinating world of revolving representation. You can do a lot with them. Thank you for watching. Like, comment and subscribe. I love you all.